to this session. We have two speakers, Punyabrata Pradhan and Davlavit. So Punyabrata will be giving the first talk. Yeah.
Thanks, but it's not moving. I can change from here if I want. Working. How it works? Okay, it's a great pleasure to be here, and thanks to the organizers, especially Abhishek for the kind invitation. So today I will talk about anomalous transport of interacting self-propelled particles. So there are interactions. Hopefully it won't be boring. Okay. So this work, today I will present mainly the sorry. Okay, so mainly I present the first one, which has been done with my student Tanmoy. He's in the audience. The second one I will try to touch upon. Third one, it is not on the archive, so we are that's in preparation. So I will be happy to discuss. Okay, so stop it. Oh, pause.
Oh, sorry.
Okay. 30 seconds, right? So these works actually have been completely done by my students. So credit goes to them. I'm here to defend. So okay. Of course, this credit goes to me. So this is the brief outline, introduction, and then I will ask how density relaxes in such processes. Then I will define bulk diffusion coefficient or collective diffusion coefficient in two paradigmatic models, run-and-tumble particles and long-range lattice gases. If time permits, I will show you the result for current fluctuations, which we have calculated from using the microscopic dynamics. And then I will summarize. Okay, so interacting self-propelled particles, they move ballistically with speed, some characteristic speed v, in a random direction, which persists for time, which is called persistence time, tau p, related to inverse of the flipping rate, I mean direction. So you can say spins is flipping or something, which again can be related to the persistence length divided by velocity. So you can see there are actually, so I'll interchangeably use these parameters. So basically the parameters here, the flipping rate, velocity, and I will talk about conserved system. So density is conserved. So density is another parameter. Okay. So let me write it down. Velocity, gamma, which is this is a flipping rate related to persistence length, well, rather I think v, right? And then density. Okay, fine. So now, so somehow, I mean, the persistent random walk, it has been studied by mathematicians since long. I mean, since long means quite long time. I mean, yeah, 3 or 4 decades before. So somehow physicists, we managed to reinvent rather, this kind of systems, which we call self-propelled particles. Of course, there are reasons. because there are many say recent experiments which actually particularly drive this field. And what is observed, I mean, almost invariably, they possess anomalous transport. For example, in some previous works, I mean, people actually have found the transport coefficient can be singular. So, which is some way manifest through the say some anomalous spread of something density or some other time integrated quantity which goes as t to the power omega, where in the normal case one would find that omega equal to half, but here omega either larger than half or less than half. And typically they have non-Gaussian distributions of something, say current. Okay, so also there are experiments in 2016 by Takatori et al. So what they found is that once the Janus particles, so they are active Janus swimmers, they are trapped in a say in a potential well, and they are released. So there are many particles trapped here, and they are released. Now they expand. But how do they expand? Well, they found quite surprisingly that ballistic propagation. So the blob, I mean, first expand ballistically, then cross over to normal diffusion. So if you see the density field, first there is an anomalous transport, then I mean normal diffusion. Okay. In another work, so which is active single file transport, by Dolai, Das, Kundu, Dasgupta, Dhar, Kumar. I think except Dolai, all are here. They studied this dynamical density correlation, so spatio-temporal 2-point correlations, and they have this scaling in certain time regime, where the growth is characterized by the dynamical exponent z, which they found numerically 1.67. So this is a super diffusive. Okay, so earlier it was ballistic, here it is super diffusive. Okay, so now another experiment, 2070, Cavania et al. They studied this experiment on insect swarm and how they spread. So they actually particularly studied this space-time velocity correlation and their scaling, and they extracted this so there is some relaxation time you can extract from the correlation function, and that goes as k to the power minus z. So k is the wave number. So and z is 1.2. So it's again super diffusive. So the current fluctuations, so they grow super diffusively. Okay, so now the question is that, I mean, what's happening? I mean, which actually, so what determines z and whether there is any universality? Of course, we found that there are several z exponents. So that's the question actually we answered. That's our motivation. And we asked this question that in the context of density spreading, so how density spreads as a function of time. So you consider a system at time t equal to 0, there is a localized thing. So you just imagine that experiment, Janus swimmers, I mean, they're trapped. Okay, so now you let them expand. So then at later times, you get a profile, density profile at position x at time t. So which governs this relaxation? So that's the question, simple question we ask. And you see, if you think that the flipping rate small or say pretty large, so pretty large in the sense the particles they flip their direction, I mean, quite often. So of course then you will find some diffusion equation, right? Well, we write it down. Del x of something. Okay, so then what will be the diffusivity? Well, if it is constant, you will put it here. But is it so? In general, it is not. So D the coarse grain density field, if you can define suitably after suitable rescaling of time and space, those are technical things. I will maybe if you have a question, I will answer at the end. So that D is density dependent. So this will come inside the first derivative and the square bracket term. So this will be the current. And diffusivity D depends on density. So all the parameters, all the other parameters actually I wrote there. V, gamma, and rho. Fine. That's okay. So that's plausible, right? And in fact, we study this limit. So that is important. So there can be actually 3 limits. So one is, first you take flipping rate tending to 0. Then you take large system size limit. What do you expect? Well, there will be dynamical arrest or some stuck configurations. So that is the thing we do not consider. Okay, fine. So that's probably Chandan talked about. Okay, jamming and also we are not considering that. The other limit is that you first take hydrodynamic limit L going to 0, system size going to 0. Then you take this limit gamma L, which now depends on the system size, that tends to 0. So that is the limit considered by Yerin, right? Or say Kobe. Okay. So now, but we take the limit L tending, so that's L tending to infinity. So this is a large system, this is coarse grain density. And then you take gamma tending to 0. Rather, I would consider any gamma. So that's important. And this is the particular case I will talk about today. Okay. So that's I have written. So there are some studies here. Right. So this is the dependent system size dependent rate. So okay, fine. So this limit 2 has been considered here. Kurban Hussain, 2018, and there are other studies too. So there are so here. So one thing is that here we are considering collective diffusion. So there is another transport coefficient which is called self-diffusion coefficient. So there you track a single particle and how it moves. In principle, they are different, but they can be related. Okay, so now we are not discussing self-diffusion coefficient. We are discussing bulk diffusion coefficient written here, D. Fine. Similar to this, our study recently, Dandekar, Chakraborty and Rajesh, they also studied it, but in a slightly different version. Okay, so they actually studied this version only, I mean this limit only, but different version in the sense. So their model. So here, what we are considering, as I told you in the beginning, the persistence exclusion process. So this is nothing but a bit of persistence random walk. So all of us, we know simple random walk. And if I ask you what is the D there? Well, there D is constant. So this is, I will say, boring. Gaussian, root T, fine. Okay, so now then you incorporate interaction. So then you go to simple exclusion process. Well, there also you can write down the density evolution equation and some miracle happens. There, this is equal to constant. SCP, what is the D? Again, constant. Well, I would not say it boring, but well, there are still interactions. So now the question is that the next generalization is this. What will happen to this D? Okay. So now these are the exclusion process and this particular reference. So they studied, so they mapped this model to a directed mass transport processes and they studied this. And in fact, we will come back to it. And what they found is that the diffusivity actually in leading order, so you are gamma tending to 0, and in the leading order, they found this is 6 eta. The important thing is which is independent of density. But then we would ask what density? That's a different model. Well, we come back to it. In fact, Rahul is there. I would appreciate Rahul's point and how the things are related to our study or the differences. Okay, fine. Okay, so now after this, actually, I have 3 important slides. All are rest are details. So rather, I will explain the next 3 slides a bit more carefully. Okay, so now we ask that, well, this problem, there are so many parameters, but what are the relevant length scales in this problem? In general, actually, it is difficult. It's a difficult problem. So what we say, we take this limit that these are things are strongly persistent. So gamma tending to 0, typically would consider, and dilute limit. Okay, so then we also take rho tending to 0. But as we see that gamma tending to 0 and rho tending to 0, they are actually not independent. So that makes the things quite simpler, much simpler than that. Okay, so how? So that I will just draw a diagram to identify the length scales. Well, so we are, say this is a typical configuration, dilute, particles are far apart, fine. So one obvious length scale is LP. During LP, I am moving just ballistically. Okay, like a bull. Fine. So one length scale is LP. So now, what are the other length scales? Well, other is that I would say that interparticle spacing maybe. So that is this. That's it. No, the most important length scale is that if I move in this direction, it doesn't matter where the other particles are except along this line. So that's the most important thing. So then how do you find the length scale here? Well, we say that the length scale is nothing but if, say, you take a snap and you see, you put an arrow, you are going to that direction and you find where the next particle is, and that is determined by the length scale in that direction. What is the mean separation, which we call the gap between particles. So in one dimension, this gap G and interparticle spacing, they are same scale, but not in the higher dimension. Okay, so we find D is a function of this. To make life simpler, we say that they have some characteristic velocity. Well, we put V equal to 1 or say V equal to some constant value and it's finite, everything fine. Then we say, well, fine. Then we find that it is a function of 2. No, I'll come to it. I'll come to it. Very good. You ask. Okay. So now, so V, I drop it from my thing that V is constant. We are not varying it. So D is this. So then we see that, well, there are 2 length scales. So equivalently, I can write D as a function of this length scale, the mean gap. I mean, whatever you say, actually mean gap. Let us say mean gap. It is not clear. Then I'll come back to it. So G bar and the other length scale LP. Of course, it is very. I mean, it is probably hopefully clear that now if you scale these 2 length scales, well, you would see the physics would be almost same, right? Except that now D will scale accordingly. So if you scale this, you get D except for this factor something, right? So well, so what it means is that D can be written as some function f with, say, you pull out some LP. I'm not using the factor, but some factor. So it has a scaling function, and this argument is independent of any microscopic details and dimension, unless you find the relationship between, I mean, how that length scale actually depends on the parameter, right? I mean, length scale will determine the length scales. So G bar, LP is fixed, fine. So then the question is, next question is how G bar depends on density and gamma. So it's very easy to say that G bar, I mean, can you guess what is G bar? Well, G bar is nothing but in the dilute limit is 1 by rho. Is it acceptable? Right. L interaction. I mean L interparticle. Right. No, finite density they will be same order, but low density they are of different order because we know L interaction. This is rho minus 1 by d. One dimension they are same, but a higher dimension they are not. In fact, that makes the whole difference. So then we claim that this argument, I mean, is pretty general. If you can identify two parameters, LP and G bar, and take the dilute density limit, this scaling function exists. And in fact, I found quite amazing that this scaling function F is not known. Please let me know, I mean, if you have some literature, but it's a well-known problem, but in this limit has not been studied before. And we are there to find out what is F. So that's the problem we are after, and we try to see what happens and what we find. Okay. Well, these arguments are, I think, well, reasonable. I mean, probably to reasonable people, but well, well, if you have objection, please, we can come back to it again. Well, once you assume, so then, well, so then another thing. So, what are the limiting values of D? Well, that's very simple. Again, there are two limits. First, you take rho tending to 0, and then gamma tending to 0. Well, rho tending to 0, first if you take, so then G bar is very large. Then you take gamma tending to 0. So LP is still much less than that. So it's a non-interacting limit. So this is a non-interacting limit. Here also things are pretty boring. And so what it would be if I plot D as a function of rho. So rho tending to 0 first. So it would be V square by gamma. Dimensionally correct, you check. It is independent of rho. Fine. Okay, so now you reverse the limit. Gamma tending to 0, then rho tending to 0. So now gamma tending to 0, then rho tending to 0. So particles will collide with each other. So that's the strongly interacting limit. Okay. So there, but in a strongly interacting limit, what is your guess? What will be your D? Well, dimension analysis will give you gamma G bar square. So you see, now you take, say you should take gamma 10, I mean small gamma. So small, I mean gamma is small. So as a function of rho at low density, I mean it's very high. At small density, I mean at higher density, it is very low. Well, what will be the function look like? The function, if you impose this condition, so the scaling function has to be like this, constant when psi equal to 0, 1 by psi square when psi tending to infinity. Okay, that I thought that a clean result. It does not depend on any microscopic details. So you take your favorite model, go to the scaling limit, and you identify the function, scaling function. Okay, so I have 12 minutes. So I think that's the message I wanted to give, and I think that's pretty clear. But well, we want to determine the full f psi, the full scaling function. Okay, so now, well, you see now microscopically, if you want to determine D, it is not an easy task. So you can, I mean, that's not surprising. So we take two paradigmatic models. One is, well, one is the RTP, what I described. So what is that model? So RTP, so you take a lattice with hardcore particle, there are particles distributed randomly with hardcore interaction, and each particle is associated with a spin variable which flips with rate gamma. For simplicity, we consider one-dimensional model. Okay. So now the particle will hop with rate 1 towards the spin direction, and if it collides with the other particle, neighboring particle, it stops. That's it. Okay, so now we see analogous model where we say, well, now if you say consider the time scale of gamma inverse. So during that time scale tau p, the persistence time, particle has already moved up, I mean, quite bit of a distance. What distance? LP distance, right? So now we define another model where there is no spin variable, but particle makes long hops with characteristic length scale LP with hardcore interaction. So if a particle makes, say, wanted to move far apart, but one particle is in front of it, it will immediately stop here. So it takes care of hardcore constant. So that's it. So these two models, they possess exactly same length scale. Now we would like to ask, what is this F psi? Well, so this model is one of the variants of model studied by Majumdar, Krishnamurthy, Barma, particular version. Okay, we also have studied the dynamical properties of this in another paper, but that's different work. So it's a snapshot with this psi variable for two different psi. You can see that there is a strong, I mean, disorder. This is a disorder, I mean, fairly disorder system, strong clustering and all. Well, so that's D. So that's the snaps you see, and they actually represent strong correlations. Okay, so now how we characterize the collective relaxation. So I will just tell you the steps in between. So first, let us take this long range lattice gas. So we have two models, RTPs and long range lattice gas. Both are interacting and all. Here, it's, I mean, quite nice that you actually can calculate this bulk diffusion coefficient. How? So not, I mean, it's very simple. So we'll have to just count. So you calculate current across a bond. How many ways it is possible? Well, many, various ways. Simple exclusion process, a current can be there if this site is occupied and this is not, and it can hop somewhere. But here there are other possibilities. So particle is far apart and this is empty lane. I mean, you have free lane. So you can, it's a long hop model, right? So it can make a long hop and come and sit here. So that also contributes to that. And you collect all the terms. So all the terms, and this is the, say, current. And current, so there is one simplification is that, so this current, so this is a microscopic current, and you can write in terms of generalized gradient. Right? So, and from there immediately you can find that diffusivity as a function of density and gamma, LP, sorry. Well, so that's fine, but still the scaling hypothesis, what we made or argued, so it's not evident from here. So for that, you have to go another step, which is that large G, I mean, dilute system, right? So the gap distribution, so say the gap is not fixed. I mean, there are various sizes. So gap distribution, it has this exponential decay. So this is also quite robust, and you find almost, I mean, various other models too. And the gap, I mean, you can see that there is a clustering, right? I mean, when you take this limit that slip rate goes to 0, so you actually create larger and larger gaps. So they are more and more clustered and create larger and larger free lanes. Okay, and that G star, so that is a characteristic length scale, which actually diverges if you take gamma tending to 0. Okay, but there is a scaling relation because the microscopic scale is set by G bar, that is the average spacing. Average spacing, I mean, average gap, that is fixed. So average gap is more or less fixed, but still there is a clustering. So you are creating more and more space. So the distribution is singular in that limit. Okay, but it's a nice scaling structure. That argument, there are only two length scale, right? G star also must depend on L, LP and rho. And we construct the scaling variable psi, which is LP by G, where G bar is connected to 1 by rho. Somewhere I wrote. Okay. G bar is 1 by rho in the dilute limit. Okay, so then immediately, but then it will depend on the scaling function, and you can calculate the scaling function in terms of this another scaling function G. And fortunately, in another work, so that is also with my students and Rahul, who is in the audience. So we found that this G, this scaling function, how the gap, I mean characteristic gap length depends on psi, the scaling variable, and it has a nice scaling property. I mean, very simple. 1 plus psi whole to the power half. Now, don't ask me how, but you can check in your simulation. Say, and it's actually quite pretty general. I mean, you take your favorite model, scale it, you will find it. We have checked many things, but I mean, we could do more. And if you plug it in, then you get this nice scaling function, which is non-singular, but and you can check the limit. What I have written here: small psi constant, large psi 1 by psi square. So it has a power law scales, power law distributed time scales. So how do you rationalize this? Well, you see there are, I mean, very what I will say, cluster states, right? So some part is quite dilute. So there are free lanes. So particle spreads quite fast, but some of the part they're actually very crowded. Particle cannot spread, and that gives rise to this power law scaling function. Okay, fine. So now, I mean, how does it explain the anomalous transport? Well, so now here, say, system is diffusive. So then how the anomalous transport would come into picture? Well, that's only because that D has a power law scaling, and you can scale your diffusion equation, scale your space and time such that you can find a scaling function which will give rise to anomalous transport, which I will show. Okay, before that, we also calculated this bulk diffusion coefficient for run-and-tumble particles numerically in simulation. So in using some algorithm, so which is something like that you create some long wavelength perturbation, and you see how it decays with time. So this decays with time exponentially, and the exponent or that factor which is called the decay rate, so that actually related to D. So we find decay rate. From there you find bulk diffusivity. So that's pretty simple, right? And you see, I mean, there are the details, but well, this we check that amplitude of the small wavelength perturbation, it goes down exponentially. Nice, pretty nice exponential semi-log scale, and you extract D. And for any value of arbitrary value of density and gamma, so that's the advantage. So you can tune, I mean, your thing, and you can check this. Okay. So now this is the plot. I have another 7 minutes, right? 8 minutes probably. Well, right, fine. Okay, so this is the plot for these two models: bulk diffusivity as a function of gamma as well as function of density. Here, I mean, I would like to show that for large gamma, it is simple exclusion. So where D you find, I mean, constant. In our simulation is actually half. I mean, well, half of probability is going to the left or right. And as a function of rho, you can see for different gamma, D depends differently as a function of rho. So it can give rise to different power laws. So that's the upshot. So depending on gamma, if gamma is too small, so then it will go to this 1 by rho square limit. But gamma is moderate. I mean, it is not that small, right? I mean, so it is competing with the gap distribution, I mean, mean gap too. So there actually you can find a different power law. So, well, I mean, if you take rho tending to 0, so then it is just flat. It's like SSCP. It's just flat as a function of rho. But here it is not. So, so the main point is that depending on flipping rate, the power law relaxation can be different. Well, if it is so, so this is the scaling. So we scaled this bulk diffusivity I mean, appropriately scaled bulk diffusivity as a function of the scaling variable rho by gamma in broad range. You can see, I mean, 1, 2, 3, 4 decades, and D varies 1, 2, 3, 4, 5 decades, and we see a nice scaling collapse in both the models. So here things are numerical. Here, here points are numerical. Line is our theoretical scaling function. Here we do not have any theory. We only know that at large psi it is 1 by psi square. So that we capture, but for small psi it actually deviates from 1 by psi square, and that's the thing. Okay, so these are details. We have checked something. I'll skip this also. I skip. So we actually did this experiment. I mean, how the density profile varies with time. So these are the experiment. We take this box localized thing, and so these are the profiles. Lines are lines are theory, points are simulation. I mean, quite good, I suppose, except at the tail. I mean, we see 2 decades of density. Well, that is another thing. I mean, that, well, let me come to the next important thing, is how the super diffusive transport arises. Can I take another minute? Okay. So super diffusive transport. So you see, earlier I showed to you that the spread can be ballistic, and we wanted to check whether adjusting your parameters such that you can reproduce that ballistic transport. So we adjusted gamma such a way, in that regime you have the dependence of density, dependence of diffusivity on density is 1 by rho form. So that you tune, right? Okay. So I mean, quite it's a pleasant surprise. So we started with some localized density profile, and let it spread for different times. You scale time ballistically, space by time, and LH model. I mean, well, you see reasonable collapse, maybe except at the tail for RTP. That's okay, because I mean it is not strictly 1 by rho, because it's slowly crossing over from one power law to another power law. So so that probably explains the deviation at the tail. But well, so the lines are the simulation, lines are the theory. I mean, if it is 1 by rho type of form, so you can actually immediately scale your this diffusion equation, space and time, such that you get the scaling function R xi of this form. So that explains the ballistic transport at the initial times. Okay. So later times, of course, I mean, it will be diffusive. Okay, so and also we checked in higher dimension too. This is for run-and-tumble particles in 2 dimensions. Well, this much we could do. And also similar. So you see, 2-dimensional diffusivity as a function of rho for different flipping rate, and we scale it. I mean, it's reasonably good. So the right panel, the scaling variable is rho by gamma, and similar scaling we have observed in other models too, like LH model. And active hard disk model. Okay. Well, so maybe another 1 minute. I promise that the current fluctuation also we calculated in these models. So actually, a broad class of model. What I mean, let me tell you. We actually proposed a truncation scheme where you can truncate the otherwise infinite hierarchy of current, density, and their moments to only current and density correlations. Using that, actually you can, well, within that approximation, you can exactly solve for microscopic current fluctuation. So I mean, how many particles moving around across a bond up to time t, which I have plotted here. That is the last slide. So well, this is a bit of digression. This is a sand pile, very interesting. I would like to discuss. So there you see, I mean, at well, this is a small t. I mean, small t means t scaled by L square. So the scale is the diffusive scale. Small t, it has root t growth for certain parameter values. So root t is normal, SCP, simple exclusion process. Other parameter values, these sand pile models. So this root t growth gives rise to anomalous growth. Okay. So this is another mass chipping model where there are correlations, and there somehow our truncation scheme is exact. In spite of there are correlation, you can see there are lines. Lines means solid lines and dotted lines, and they exactly fall on each other. This Q square. Okay, this is for the long range lattice gas. We calculated Q square, the bond current correlations or time integrated bond current fluctuations as a function of time, and it has similar thing, and there are singularity. I mean, this feature, see, actually it gives rise to root T growth to some other growth, and that growth actually is very important. And in fact, in this model there can be singularity. We can discuss it later. Well, I think I'll stop here. Summary, we argue that bulk diffusion coefficient depends on a single scaling variable in the low density limit in the interacting self-propelled particles. We calculate the scaling function in two paradigmatic models of the SPPs. In different density regimes, density relaxation can exhibit super diffusion in certain cases, even ballistic transport, due to this power law dependence of diffusivity on density. And our arguments, we believe, that are independent of dimensions and microscopic details. So thanks for your kind attention.
Yeah, and the question is, what makes these long hops? So I'll make a comment also. In hydrodynamic turbulence, this stellar diffusion is the exponent is 3/2, and there the hops are by the vortex of different sizes.
Right.
Do you see something like that? In this you are not. I don't know.
No, I mean, we have not checked it. I mean, no, people actually have seen these vortex. I mean, it's turbulent, right? Turbulent flows in active matter, but I'm not very familiar. I mean, one could actually, people say about that turbulent motion in active particles, active matter systems. I think Sriram maybe or Abhishek, they know better. But people have found it.
What is leading to long hops for you? You are conjecturing it, or
no? The long range model we are conjecturing on basis of the RTPs, because see, it's an active matter. I mean, the self-propelled particles, if it starts going to some direction, it will persist. So it's a long hop, right? So
Punyabrata, I have a small question.
yeah.
There was a plot in
Yes.
which you had a scaling half minus mu. Yeah, that mu.
This one?
Yes.
Right, yes. But
So-
this is hand pile, digression, but well.
But
fine.
that mu is known, kind of.
No, mu is not known. This is, well, mu is known. What do you mean by known? I mean, we found it, and we
Okay.
have also some scaling theory where we actually calculated mu in terms of the critical exponents.
Okay.
Right. Well.
Okay. Okay. So let's thank Punyabrata. And next talk is by Davlavin. Okay, so Davlavin is going to talk about random closed packs. So
Sorry, Deepak. So I'd like to thank the organizers for inviting me. It's a delight to be here in this auditorium celebrating Deepak. And I love this blackboard. And I remember a few years ago starting there and filling it up to there. And it's just a delight. So what I want to tell you today, as Sriram said yesterday, when he already spoke, was now for something completely different. Okay, so this is going to be much more of a soft matter talk, and so hope you like it, as they say. Okay, so the question is, can we define random close packing? And this is work done with Paul Chaikin at NYU, his former student, now a postdoc at Santa Barbara, Sam Wilkin, his former postdoc, now at Impossible Meat, I believe it is, Rodrigo Guerra, which is, I'll tell you later, Shuna. And current postdoc of ours, Ashley Woe. And so, yeah, there we go. So the general question is, what's the densest packing of identical spheres? And so there we go. So in MDCXI, Kepler wrote this book, and in it, he conjectured that the densest possible packing of spheres was in this arrangement that we see over here. Now, that was 16 something or other, I forget when, 1611, thank you, Sriram. 1611, and well, before I tell you more about these guys, the arrangements that Kepler was proposing have a volume fraction of 0.74, just that number over there. There are various periodic arrangements, FCC, HCP, there are other stacked arrangements, doesn't really matter. Those are the two best known. Cannonballs, this is a useful talk, okay? So that was 1611. My guess wasn't that Kepler was the first, but he was the first to write a book on it. But I don't know. I say, okay, you give me the reference, Paul, and I'll put it in. In any case, however that might be, it took another 200 some odd years for Gauss to prove that indeed was the densest lattice packing, crystal packing of identical spheres. So Gauss proved it in 1831. The two-dimensional problem is much easier, okay? This is actually quite difficult. And it took another 170 years roughly for Thomas Hales to prove that this was in fact the densest packing of identical spheres of any type, whether it be lattice or disordered, if you like, okay? And that was quite a tour de force. The Fields Medal this past year was given to a mathematician who proved the same thing in 8 and 24 dimensions. These are special dimensions. And so this was, she won the Fields Medal for that. It's again, these are tour de force pieces of work. Good. But this isn't what you get if you pour ball bearings into a giant container. Then you get something like this. Well, these aren't ball bearings, they're marbles. And it used to be that you'd go to various carnivals when one used to go to carnivals, when there used to be carnivals, And they would have some big thing set up like this, and you had to guess the number of marbles in there. And if you guessed it, you won a cat or something. You won something. Okay, I mean, guessing it, get the closest one to it, and so, and this arrangement, and how do you get it? Well, what they get is pour these things in under gravity. There are other experimental methods, typically involving pouring hard spheres into some container, shaking them, jostling them, treating them badly, and then they densify until they get to this random close packing state. And it is typically the case, almost always the case, experimentally pretty much always the case, that the density, the backing fraction of such an arrangement is around 0.64. Okay, so the question is you can ask why 0.64 if you like, and that's a perfectly legitimate question. Bernal studied this in 1960. Scott studied it in 1960 at the same time. Sid Nagel revisited the problem in the late 80s, early 90s, probably early 90s, and they got the same density. So this seems to, so the lore is that basically no matter what you do, you pour a bunch of hard spheres into some container, and provided the container is large enough, this is the volume fraction you're going to get to. Okay. So the question is, I mean, so how can we define something like that? It's easy to define a crystal packing. Anything with order, you say, well, I'm looking for an arrangement with this order, right? Some sort of broken symmetry. I identify it through a broken symmetry, so I sort of understand how to do that. If I don't have any such thing, then I don't know how to define it. So fundamentally, how do you define something, some configuration, which is sort of defined through the absence of equality? And that's the question I wanna place in front of you and try to give you some sort of an answer. Anyway, there have been a couple of attempts to discuss this. Torquato and his collaborators proposed that you can define a what is equivalent. They give a different name, but the equivalent of random close packing of hard spheres by looking at a set of order parameters and looking at the packing which minimize them. The problem with that is there are always other order parameters which you haven't thought of, right? And so this can't serve as a definition. Other people, O'Hearn et al. And other people have proceeded with that as well, have said, well, what's actually happening, the reason you always seem to see this is because the basin of attraction of the set of when you started some configuration and you do whatever dynamics it is which is going to lead you to the packing, the basin of attraction of 0.64 density arrangements is the largest. That's what they would say. But that sort of depends on how you do the simulation and what the protocol is, as Shrikant knows better than anybody else. So you have to. So this wouldn't serve as a definition either, although it is certainly very nice. Okay. But I want to make contact with what people seem to think is random close packing. So I have to tell you a little bit about how people get them. So the most common algorithm is the Lubachevsky-Stillinger algorithm. And what they do is as follows: they start with a bunch of point particles. Let's say, I don't have to do it this way, but it's easiest to state this way. Start with a bunch of point particles which have some sort of energy to them, so they're moving around. Okay. And what you do is you swell the particles at some rate, and eventually they will jam and they won't be able to move anymore. So the parameter, given that you have a certain energy defined, is the swelling rate. And the thing is, if you look at the as a function of swell rate, the ultimate density that you find is dependent on swell rate. If you swell it too fast, then you get a lower volume fraction. If you swell it too slowly, you get a higher volume fraction. And so what you do is you stop the simulation when you get to where you want. And I mean, you say, well, I'm going to look, I know where I want to get to, and I'll fine tune this flow rate. So that is, again, not very much of a definition. You have to avoid certain things by hand, like crystal regions. Okay, so what's known about RCP? Very quickly, RCP configurations are isostatic. That means they're minimally stable. Now, the way you would, I suppose you could say there's the same number of constraints as degrees of freedom. Each sphere has 3 degrees of freedom in 3 dimensions. And therefore, there are 3n. If you have n spheres, 3n degrees of freedom. I'm not worried about the minus, about subtracting out the overall translations. The rotation doesn't bother me much. So if the jth sphere has z sub j contact points that are constraining its motion, the total number of contact points is just n by 2 times the average of j, because each contact point is shared with 2, factor of a half. So there, if I want these two to be equal, then what I find is that the average number of contacts should be 6. That's called an isostatic packing. In more generality, in d dimensions, you just get twice the dimension. It's different if you have friction. Okay, if you have friction, it's a different story, but there's no friction here right now. Okay. Other thing you can look at is the pair correlation function. People often look at that as a means of understanding the structure. And what this pair correlation function is, just for those students who are new, it's the probability of finding a pair of particles some distance separated by some distance. And so you can't, of course, have, if these are hard particles, you have a hard cutoff on the left. There are a couple of, I don't know if I have a laser pointer here. Do I have a laser pointer? Yeah. There's a characteristic feature of this split second peak, which looked like Batman or something like that. And the other thing is you have a characteristic drop off from touching. Now that goes by the name of, so if this measures the gaps, okay, between the spheres. And so I'm going to come back to this. This decays with a power law, and according to this group a long time ago, the gap exponent, what's called now the gap exponent, is minus a half. Okay, yeah.
Is there a delta function at 1?
Is it a delta function at 1?
In G of R, is there a delta function at 1?
Is there a delta function at 1?
Because you said there have.
I think there has to be, right? Well, does it have to be? Yeah.
Okay. And then there is still some region in which it is not 0 immediately after.
I mean, to the extent that, you know, to the extent that people do simulations and of finite size, I think that's the case. No. Yeah. No. Well. Oh, it's diverging the other way. Yeah. Diverging the other way.
Strange to me just now.
Hmm?
That sounds very strange to me, but we can discuss later.
Okay. In any case, this is so I'll come back to that point a little bit later. So we saw some years ago that this fell off with a characteristic power of half. Okay, and we'll come back to that a little bit later. Okay, so basically, would say, I mean, on the minimal aspect that the minimal things that you demand from something which claims to be random close packing is that it be isostatic and that it have a G of R, which looks like that with whatever characteristics you can derive from those points. Okay, so let me now switch gears and tell you about a model called random organization. I'll do it rather quickly. It's an absorbing state dynamical model. So this is why perhaps it's appropriate to this meeting. So in random organization, the simplest possible model is, this was a model Paul Chaikin came up with to understand some data on sheared non-Brownian particles, Dave Pine and Jerry Golub. In any case, you have the system is like this. You put particles down at random. They have a finite size. If they are alone, you don't do anything with them. And if they overlap, you give them a random kick. You just randomly move them. Okay? Some amount, some distribution. Take a flat distribution between 0 and some maximum, whatever it might be. Okay? That maximum kick size is in fact a parameter in the model, and it will change certain things, but it won't change the more interesting things. And you're going to continue this until there aren't any active particles or until the activity level's off. And as Sriram and Gautam Menon showed a while ago, this is an absorbing state model in the Mana universality class. Okay. And here, this is just because to show you that I know how to do minimal programming in Keynote. For this particular example, if there are more than 2 particles in the box, let's empty the box and redistribute the contents randomly to neighboring sites. So I'll do that, and I'll do it again. And I mercifully didn't do too much. And now everybody is happy because everybody has fewer than 3 balls in the box. So this is now an absorbing state. Dynamics is over. Had I put more in, the dynamics would continue. Had I put sufficiently high density. Okay. So a sufficiently high density is in fact something above what I'll call rho C, which suggests to you that which you already know, that this is a critical density. The fraction of sites or a fraction of balls which are active is the order parameter in these transitions, and you have the active fraction as a function of density is 0 in the absorbing phase, of course, and then it rises with some characteristic exponent close to rho C, and this is all well studied for a variety of models. Okay, the interesting thing, as far as I'm concerned, is the fluctuations in particle numbers, something I talked about a couple of years ago here. Probably here, and certainly at the IFR. For a random distribution of points, the variance of the number of particles in a window of size L, so I'll take it to be circular here, it doesn't really matter, scales as L to the power D if I'm in D dimensions. On the other hand, if I have a crystal lattice, and to make life easier, I'll just slightly shift all the points just to avoid having any issues. The variance scales as L to the D minus 1. Okay, so you would say, well, generically, the variance might scale as L to the D minus alpha. And then if alpha is less than 1, your distribution is less than perfectly random. Okay, and what we found was with Daniel Hexner a few years ago, was that the critical states of this class of models had that property. The variance in the number fluctuations was less than random, more than periodic, but less than random. That is to say, alpha was positive. So this has reduced fluctuations at criticality, and this is called hyperuniformity, typically. And the values of alpha are characteristic of the Mana class. So you can use different models and you'll get the same values of alpha. It's, of course, dimension dependent. Okay. Here's a picture of a critical state from the random organization model in 2 dimensions. And here's just some random non-overlapping or not particularly overlapping set at the same density set of disks. Okay, that's fine. You can also see this in the structure factor, which is effectively the square of the Fourier transform of the 2-point function. And the only point I want to make is that you see hyperuniformity through the structure factor if the structure factor at small k, that is to say large scales, large real space scales, small k goes to 0. Now, for me, I'm only going to think about cases where it goes to 0 as k to the power some power. And as it happens, that power alpha is the same alpha that we found a second ago. Okay? In other words, these two things are connected. So the structure factor and the number of fluctuations are connected. They have the same exponent, although they come in different ways, of course. Okay. Good. Now, let me change the model just a little bit, and we'll bias things a touch. Before, when we had overlapping particles, we moved them at random. Okay. Now I want to bias them to move apart a little bit. So they move apart a bit. They also have some, in principle, they have some amount of random motion as well. Okay. Excuse me. The maximum displacement is epsilon. Delta tells you how much randomness I have. So and it goes between 0 and 1. So this is now what it looks like. If delta equals 0, we get back to the previous model. Okay, delta equals 1 just separates them with no randomness, and the critical behavior. I'm not going to show this to you. The critical did quite a bit of work to show this. The critical behavior is the same as the mana, as the regular random organization model was, which is the mana class. Okay, and in particular, that exponent alpha, which characterizes fluctuations and decay of the structure factor, is about a quarter. Okay, just to make that, talk about that later. Okay, so what do we find for critical states in this model? Well, in this model, it depends on how much randomness you have and how large the maximum kick is. That's also true, by the way, for the random organization model. If I move particles further, I'll eventually come to a critical density, and the critical exponents are the same irrespective of the value of epsilon, the kick size that I choose, but the densities are different. So it's sort of like, if you like, you change things up on the Ising model, the critical temperature may change, but the exponents don't. It's the same sort of thing going on here. The point is that as the maximum kick size, epsilon, goes to 0, these guys seem to converge to the same critical density. So we've only shown it for you can see it for the blue and the red curves. The others will join it as well, except for the bottom one, which is just random organization. It's flattened out. It's going to stay there. Okay. So it doesn't matter how much randomness you have. In the limit, as the kick size goes to 0, you tend towards critical states whose density is about 0.64. Okay. Then we looked at the structural characteristics. So this is what the pair correlation function looks like. Has very similar. It looks very similar to what I showed you before, and in fact, it does. I mean, when we overlaid it, I didn't do it here as a limit to how much one can show. It overlays nicely on what's generally accepted as random close packing. So from other methods, so things are okay. Has that Batman second peak in the limit of small epsilon, and in addition, so have I run out of batteries, or is it? Come on. Yes. That was that. Good. It has that 1/2 slope, or that exponent of which scales, the gap exponent scales the way I showed you earlier as square root. Okay, so we were happy about that. So we then of course what's the thing you declare victory and retreat? Is that that's the usual way of doing things? So we declared victory, but then we didn't quite retreat just yet. So let's look at the structure factors. So this is S of Q or S of K. I've overlaid 3 different ways of arriving at these random close packed states. They overlay quite nicely. It's a logarithmic plot. It's a log-log plot, which is important to do. And this comes in with an exponent. So S of K goes to 0 as K to the 0.25, which is the same as the mana exponent that I claimed before. The exponent, the hyperuniformity exponent for the mana class that I claimed before, I should say. There we go. So what about other dimensions? I might actually finish, in time. This is going to be, there should be a prize for that. Good. What about higher dimensions? If we want to make the claim, which we do, that, well, so before I talk about higher dimensions, the declaring victory is now to say the following thing. It's to say that we propose that random close packed structures are the critical configurations of a well-defined dynamical model in a well-defined limit. Epsilon goes to 0, biased random organization, starting from a random initial conditions, because people know if you start from a carefully chosen initial condition, you can get different things. So this is the measure 1 answer. And so if we're right, this would provide a definition of random close packing, which of course circumvents the necessity of discussing what's random and what's not random, which is a fool's errand. There's no way we could do that. Why would you care? Well, aside from the intrinsic amusement that we get from it, it suggests, if this holds in higher dimensions, that you could, in principle, try to get results from higher dimensional systems. Okay, and then maybe one can actually do something analytical with this problem. Okay, which seems otherwise pretty hopeless. Okay, so what about our other dimensions? Well, so as a function of epsilon, so let me just point out there's a bunch of things going on here. D equals 3, I've already showed you. Now what we're doing here, this is a critical volume fraction as a function of maximum kick size. So that changes, as I told you. If you kick things more violently, you'll eventually come to there will be a critical state, okay, separating active and absorbing, but it will be less dense than something which is kicked more gently. Okay, and we're looking again in the small kick limit, and the epsilon goes to 0 limit. So D equals 3, I already told you a bit about. So that's over here. So as epsilon gets smaller, the critical, so each of these is a critical volume fraction of a critical state at these different maximum kick size. Okay, and it's quite nice if you plot it logarithmically, things flatten off. But here you can see that things really tend linearly to a well-defined volume fraction, as I told you, was 0.64 in 3 dimensions. In 1 dimension, shockingly enough, it tends to 1, because sort of what else could it do? Okay. 2 dimensions, it tends to 0.91. 0.91 is maximum packing of identical disks. And the reason I even bring this up is because there's a lot of discussion recently on whether or not you have random close packing in 2 dimensions, random close packing of identical disks in 2 dimensions. And people have religious fervor about it. And so in the interest of religious wars, we want to come out and say that these don't exist, that there is no random close packing of disks, and and then get attacked. But that's okay. So that's the point about D equals 2. What about D equals 4 and 5? So D equals 4 and 5. Again, behavior looks similar, and you cross over, and you get a critical density of around 0.46 for 4 dimensions and 0.3 for 5 dimensions, which are consistent with other algorithms done by other people. I'm really fine. I'm speaking slowly because I just don't want to. Hang on. Oh, you can ask a question. You can screw me up.
Yeah.
Speak up, seriously.
Did you
Right.
try polydispersed disks in 2D?
2D, yes.
Polydispersed.
Pardon?
Polydispersed disks.
Yes, we did.
Okay. You're going to.
I mean, they obey the same sort of things that they should. They fall into mana class. They have the right gap exponent, all this stuff. But I don't want to get it. It's a bit too technical. Yeah, but we did. Is not? Sure it is. The limit exponent for bidispersed or polydispersed. Sure it is. Yeah. They won't, but we won't get to those packings. No, we won't get to those packings. No, we won't get to those packings. No, it's not perfect in the sense that it's not crystalline, right? It's not even the densest possible packing. We get the density of what's conventionally called random close packing. Oh no, 0.9, no, 0.91 in 2 dimensions is a crystal packing. In 2 dimensions, I'm sorry, in 2 dimensions, yes. No, I don't believe that if you give me a random distribution of disks in 2 dimensions that you'll always get the most. No, I don't. That was, I guess, the question. Might have been the question. Oh, okay. Was that your question? You might as well say yes, because, okay, very good. So yes.
One more question. Is there a proof that this linear extrapolation is exact?
No. I mean, you could have stopped at is there a proof, and the answer would have been the same. Irrespective of the continuation. Okay, so those guys are periodic, right? So those guys, the 1-dimensional, 2-dimensional packings that we get are periodic. And now I'm just talking about the gaps again. And so the gap is the closest approach to particles we'll have. Okay, and it was shown by Charbonneau, Foche, Korchan, Giorgio Parisi, Urbani, and Zamponi that in a really rather tour de force calculation, full replica symmetry breaking calculation in infinite dimensions, that that exponent, that gap exponent that I previously told you was 1/2, was 0.41 roughly. Okay, so this is a calculation which is really quite glorious, and it gives you a number which is really quite nice. Now, several of these people claim that this is true in all dimensions, that you get the same number for all dimensions. I want to dispute that, but I'll do that in just a second. Okay, so let me just look. So here, let me dispute it right now. Okay, so I've shown 2D, 3D, 4D, and 5D, and it would work by the, sorry, 2D, yeah, 2D is a bidispersed. Shrikant, wake up. This is 2D is a 2D bidispersed. Okay. And the values of gamma, that gap exponent that we find, is in 2D 0.58, 3D 1/2, as I argued before. 4D and 5D is spot on to where these folks predicted for the infinite dimensional case, okay, which is quite nice. We've modded all that the behavior out. So flat means at that exponent. Okay, so this is what we say. And then you say, well, what about hyperuniformity? So, okay, let me, I'm going to blow my, I'm going to really blow it. I'm going to, it's trying to get under. No, it's because of the questions. It wasn't because of me. I would have easily made it. In any case, so the three-dimensional, I've already shown you that the three-dimensional random close packed structures that we get, and as I said, they match. This is also true for RCP structures that are obtained by, let's say, LUBACHEVSKY-STILLINGER. We have some people are kind enough to give us, I have 35 more minutes. I'm fine. Yeah, this is the problem with ADD, is now I don't know where I am. Thing rings and I'm gone somewhere. So I showed you that in 3 dimensions, the packings are hyperuniform. I told you what the exponent was. Okay. In 2-dimensional bidisperse, they're also hyperuniform with the expected monoclass exponent, which is some years ago, we conjectured, again, not proven, that the hyperuniformity exponent is 2 minus the correlation function exponent. Seems to fit. That's the and so this works in 2 dimensions as well for bidispersed systems. Of course, monodispersed disks is a different story. And if you look at that, so the mean field value of that correlation function exponent eta perp is 2. And in that case, you'd expect alpha equals 0 above 3 dimensions, d equals 4 and above. And sure enough, we find that you get that exponent for 4 and 5 dimensions. What does that mean? It means that those packings are not hyperuniform, which is sort of you might argue it's a very strange thing. So in 3 dimensions, you have a hyperuniform random close packed structure. 4, 5, 6 to infinity, you don't. They have random fluctuations, and so that's sort of an odd thing. So the point is that we're claiming that that 4 is the upper critical dimension of random close packing. In this sense, right? In the sense that we can, and this follows from our identification of the configurations as being those of the critical states of this model. Okay, so that's sort of an amusing thing, and that's consistent with what I showed you a second ago. 1 second, Shyam. That's consistent with what I showed you a second ago about the gap exponent. Okay, being different from 0.42 in 2 and 3 dimensions, despite claims in the literature to the contrary, and being 0.42 in 4 and 5, and we'll eventually look at 6, 7, and depending on how many students we have, and how highly we regard them, 8, 9, 10. There we go. So let me conclude. So these are the declaring victory and the retreat part. So RCP, we claim, can be defined as the critical states in the small kick size limit of a well-defined absorbing state model called bias random organization, which is in the Manna universality class. Okay, that's the claim. In 3 dimensions, random close packing is hyperuniform with characteristic exponent of that class. The upper critical dimension of RCP is 4, consistent with the Manna class. And we get the correct, or correct in the sense that they agree with other people's work, densities in 4 and 5 dimensions. And in 1 and 2 dimensions, we only get periodic lattices. So we're going to now go out on a limb and say that there isn't random close packing in 2 dimensions, they say, because we want to make our friends dislike us more than they already do. And what that would say is that, that 3D random close packing is the least random of the random close packings, in the sense that it's hyperuniform. All the other ones are not, or they're periodic. Thank you very much, and I'll try to answer.
Hello. Hi. So you had a graph of the G of R versus R, and it had singularities at 1 and 2 and √3 and various numbers. Are the nature of singularities other points also known?
I don't think anybody studied them.
Okay.
So yeah, I don't think anybody's.
It looked like they were singular at other points.
They may very well be, and I mean they do have that. Yeah. I don't know of anybody who studied that, but indeed they do look cusp-like. Yeah, that's.
So
yeah.
those cusps. Sorry. So those cusps, those Batman's cape things, they're special to 3D.
Yes, as far as I know.
Okay.
I believe that's true. I mean, it could be that people weren't able to generate packings large enough in higher dimensions. So you don't see it in 2D, in higher dimensions. But the pair correlation functions I've seen from higher dimensions don't seem to show that.
So which will be the protocol which is consistent with this definition experimentally? You just pour it, or you have to shake it, or?
Yeah, you shake it. You pour it in. You shake it, right? You don't know. So what are you nodding then for? I'm shaking, not stirred. You pour it in, and then you shake it a bit, and yeah. I mean that's more or less what. So that was done by Bernal. It was done by Mason. It was done by Sid Nagel, and collaborated, and Heinrich Jaeger and people working with them.
All get 0.64 plus
They all
minus,
get
plus
0.64,
minus
yeah.
something.
They all, yeah. The system, ultimately, they start out. It was so in Sid's case, he started them out from a denser, from a denser arrangement and a less dense arrangement, and he banged them around a little bit, and probably systematically, and he found 0.64. Delta is provided by, well, something's provided, I don't know, delta is provided by gravity, but maybe.
Hello.
Yes.
And there also, if you vary the rate at which you inflate, that takes you to denser systems, right?
Mm-hmm.
This limiting procedure doesn't work there, or?
Which doesn't?
This limiting procedure, that is, if you actually look at the density as a function of the rate.
Which limiting? I mean, so in Lubachevsky-Stillinger, you have what's the word?
Inflate the individual spheres, right?
Yes.
And but the rate at which you do that depends on where you get stuck.
So you change that, you swell at a certain rate.
Yes. As you go slower, then you go to higher density.
As you go slower, you go to higher density. Yes.
I mean, if I look at the limit of that, then.
Oh no! If you go to the limit of that and you do it right, I think you crystallize pretty well.
I see.
I mean, you may not get a perfect crystal, but it crystallizes in the sense of crystal regions.
Now, with the Lubachevsky-Stillinger procedure, you do get RCP, except they didn't want to say so. I think. So, I mean,
they know that?
they do get 64% with from the work of Torquato et al. Yeah, I don't think there's any problem there.
No, there's no problem. But if you swell too fast or too slow, you get something else.
Too fast, yes.
Yeah, and
Yeah.
too slow.
Yeah.
It's not. You can't do it infinitely slowly and expect to get as far as I know. Sir.
Each of them are doing a random one, very small amplitude random. Then I increase the number of this Here's in the system. Whenever there is a vacancy, I add one. And it also starts doing random one. Then by chance there will be another vacancy, I add another one. So could that be a possible way to generate
I don't believe it, but it would be, but it's a cute model. I like it, but no, I don't believe you'll get I don't think so. Yeah, but if you have to wait infinitely long because everything is going to open up, yeah.
So can I? The last part where you talk about the GFR exponent, that's both surprising and, as you said, it's inconsistent with what people have found in 2 and 3 dimensions. And not only the GFR exponents, but also the relationship with the exponent that Chandan talked about for the force distribution. So the gap on the force distribution exponents satisfy the marginal stability condition that has been expected, and both the exponents are calculated in the mean field theory that you mentioned. I think, and something that we have done is to also show that this is even valid for shear jamming, which is not something that was originally part of the theory. So I think that exponent being 0.4169, whatever number you put up, is fairly well established at this point.
No, I don't think so at all. I mean, it's certainly, it's
D equal to 2 and above.
No, it's certainly not. It is certainly not well established. And if you look at the data presented, it's not. We can have a discussion, but well established, it is certainly not.
So I had 2 little questions. One, where is, at the end of the game, where is isostaticity in the whole story?
Where is it? It arises as
meaning you can measure the resulting configurations by, I mean, the configurations at this critical state are in fact isostatic.
Yes, indeed.
Numerically measured, you're saying.
Yeah.
Right. Other thing I didn't understand, I mean, why is this, you must have said it, why is the biased process necessary?
Oh, because otherwise you'll get,
I just missed
you'll get a maximum density no matter what you do, which is much lower than random close packing. Right? You'll have, you won't get things which are touching in the same way. Certainly it'll be far beneath isostatic.
I see. But whereas, okay, if you look at the original experiments by Dave Pine, they were done by shearing stuff in some oscillatory way and things.
And they're done by jostling and banging them, stuff like that in the experiments.
Oh, that way.
Yeah. They put them in balloons and massage them. This is literally what
the dense ones. I was thinking of the sheared random organization ones. I guess those.
No. That's a different story. Yeah, there's no.
There's absolutely no contact between that and this.
Well, I mean, the same model generically, same critical exponents, of course, but no, there's no sense in which there's no shearing involved here.
No, you couldn't. Yes. No, I'm talking.
I know. We know.
Yeah. No. What I meant basically was doing those experiments at progressively higher volume fraction. In the shared way, I mean. So it seems that if we put in a protocol of shear in 3 dimensions, it crystallizes. That's all I can tell you. That's all I can tell you. So it wouldn't give you. Yes, Shrikant.
Yeah, no, the other point about these GFR singularities, something that we looked at some time ago was what happens when you athermally shear spheres, and all the GFR singularities you develop, regardless of whether the system is jamming or not, right? So it seems to be more a consequence of a certain way of bringing particles together, rather than whether it has anything to do with jamming physics. Okay, this is.
But if you have an equilibrium fluid of spheres, you don't get a.
Yeah. No, I said athermal shearing of spheres.
Okay, fine.
Yeah.
Okay.
So it's and
if
I'm not mistaken, though I'm not 100% sure. The second peak simply corresponds to sort of tetrahedral and octahedral arrangements. So there's a corresponding, yeah. So I think these are just sort of, Kabir may have something to say about this.
That's true. There, you have local because.
So these are very local features.
Yeah.
On the other hand, the GFR singularity at 0 or at sigma that you're surprised about, that does seem to be a non-trivial feature. It does arise even in non-jamming contexts, like I mentioned, but that sort of has to do with progressively pushing particles out of overlap, but then you always do it in the least possible or least necessary amount, which leads to a pileup of near contact neighbors.
Can I ask a question from here? Sure. This is trying to answer the question of what's the protocol. And I'm trying to find it. There appears to be, in the old days, there was a protocol known as Baker's protocol. How bakers make cakes and stuff. I'm trying to find it on the net. There appears to be thousands of references to Baker's packing protocol.
Baker's map.
Okay, so no, this is a baker meaning a bakery.
Yeah, but the Baker's map is exactly that.
Yeah,
but
yeah.
It's a,
So there is a protocol apparently. And they have been known for centuries of how to get bakers. This is what it's showing. But anyway, so that's one question. The second question was, in the old days, the liquid, if you just looked at a regular liquid and did a structure factor thing, in your Pac-Man, that Pac-Man appears to be very sharp, pointy things. Is that important, or it could be?
it seems to be characteristic.
And it's a cusp with definable things.
I haven't looked at it carefully enough to make a statement like that, but on a
in
cursory viewing, it looks.
Yeah, we used to usually define that appearance of the split double peak.
Yeah.
Second peak as the appearance of a glass. And this was very, very old times. And I don't know what that reason was.
Say about it is we long ago looked at the second peak in hard sphere fluids below the freezing density, where the peak begins to split. And this was surprising precisely because of what you said, which there was the folklore that, I mean, there is some connection to the emergence of glassy behavior, because what it reflects is the onset of well-packed structures locally, right? But that happens in hard sphere fluids below the freezing density, which is clear proof that it really has nothing to do with glassy behavior, right? But you should also expect it in glasses because they are energetically stabilized compared to the fluid.
Okay, I just had a question about the hyperuniformity. Do other ways of constructing random close packings give the same hyperuniformity exponent?
Empirically, yes.
Okay, so
Yeah.
it does appear to be in the Manna class, even independent of constructing it via a Manna kind of process.
I mean, but there you have maybe 2 data points, right? Because you have 2 dimensions and of bidispersed, let's say, disks, and then you have monodispersed spheres. So you can conclude what you'd like to conclude, but it's certainly suggestive.